Everything we know about the world is currently stored on something physical. While we often speak of the cloud as an abstract, weightless place, it actually consists of millions of miles of fiber optic cables and massive warehouses filled with humming machines. Human history has always been a quest to find more efficient ways to record our thoughts, moving from stone and parchment to the silicon chips that power our lives today. But we are reaching a physical limit with our current technology, forcing us to look toward the most efficient storage medium ever discovered, the molecule. The story of modern data storage doesn't begin with electricity, but with silk. In the early 1800s, Joseph Marie Jacquard invented a loom that used stiff cards with punched holes to automate complex weaving patterns. Each hole represented a physical instruction: either the thread goes up or it stays down. This was the birth of binary logic. By the mid-20th century, these paper cards became the primary way humans talked to computers. Information wasn't a signal and a wire. It was a physical absence of material, a hole through which a machine could sense a truth. In 1956, IBM introduced the 305 RAMAC, the first computer with a hard disk drive. It was roughly the size of 2 large refrigerators and weighed over a ton. Inside, 50 massive aluminum disks coated in iron oxide spun at high speeds. Despite its immense size, it could only hold 5 megabytes of data, barely enough for a single high-resolution photograph today. At the time, this was a massive leap forward. It moved us away from sequential paper tapes and allowed the machine to jump directly to any piece of information on the spinning platters. For the next 60 years, we refined this mechanical approach. We learned how to polish these metal discs to a mirror finish and fly a magnetic read-write head just nanometers above the surface. If that head were a Boeing 747, it would be like flying a fraction of a millimeter above the ground at full speed without ever touching it. By shrinking the magnetic regions, or domains, we packed more information into the same space. However, these spinning platters are prone to mechanical failure and consume significant amounts of energy just to keep rotating. Eventually, we moved away from moving parts entirely. Solid-state drives, or SSD, use a technology called flash memory. Instead of magnetic grains on a platter, they use tiny transistors to trap electrons behind an insulating barrier. This creates a state of charged or not charged, representing our ones and zeros. Because there is no physical arm moving back and forth, data can be accessed almost instantly. This transition allowed our devices to become thinner and more durable. But silicon-based storage still faces a fundamental problem. It eventually wears out and requires constant power to maintain. The sheer volume of data we generate is now outstripping our ability to build enough silicon chips to store it. Every video uploaded, every medical record, and every scientific observation requires physical space. Estimates suggest that by 2040, we will not have enough microchip-grade silicon to keep up with the world's data demands. This has led researchers to look at the most compact and durable storage system in the known universe: deoxyribonucleic acid, or DNA. Nature has been using this liquid-based coding system to store the blueprints for life for billions of years. DNA is essentially a biological hard drive. Instead of the binary system of ones and zeros used by computers, DNA uses a quaternary system consisting of 4 chemical bases: adenine, cytosine, guanine, and thymine. Scientists have developed algorithms that can translate any digital file, a movie, a book, or a software program into a specific sequence of these 4 bases. Once the sequence is determined, synthetic DNA is manufactured in a lab, creating a physical strand that contains the encoded information. This process turns digital data into a shelf-stable, organic molecule. The density of DNA storage is difficult to visualize. In a traditional hard drive, data is spread across a 2-dimensional surface. DNA is 3-dimensional and incredibly compact. Theoretically, a single gram of DNA can store about 215 petabytes of data. To put that in perspective, every bit of information currently on the internet could fit inside a container the size of a standard shoebox. A teaspoon of this liquid could hold the entire history of human knowledge and still have room to spare. It is the ultimate limit of data miniaturization. Beyond its density, DNA is remarkably durable. Magnetic tapes used for long-term archiving usually need to be replaced every decade to prevent data loss. Silicon chips can degrade over time due to heat and moisture, but DNA, if kept in a cool, dark environment, can remain readable for thousands of years. We know this because we have successfully sequenced the genomes of woolly mammoths that died over 50,000 years ago. This makes DNA the perfect candidate for cold storage information that needs to be preserved for future generations without constant maintenance. The process of reading the data back is surprisingly straightforward. Using existing technology developed for medical diagnostics, scientists can sequence the DNA strands to determine the order of the chemical bases. A computer then translates that sequence back into binary code. We have already reached a point where we can store and perfectly retrieve 4K movies and entire operating systems from a drop of liquid. The bottleneck currently lies in the speed and cost of writing the DNA, which is still much slower and more expensive than traditional manufacturing. As we refine the chemistry of synthesis, the cost is dropping. We are moving toward a future where data centers might look less like warehouses of metal racks and more like pharmacies filled with climate-controlled vials. This shift would drastically reduce the environmental footprint of our digital lives. DNA storage requires no electricity to maintain, produces no heat, and is entirely biodegradable. It represents a move away from the extractive industry of heavy metals and toward a more harmonious relationship with the biological principles that govern the natural world. We are coming full circle. We began by using mechanical looms to weave patterns into fabric, and now we are learning to weave information into the fabric of life itself. The transition from the massive, spinning platters of the 1950s to the microscopic strands of DNA is more than just a technological upgrade. It is a fundamental shift in how we perceive information. Data is no longer something we just store on a machine. It is something that can be held in a drop of water, lasting long after the machines have stopped humming.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.